Okay, so Rahul will talk about a very interesting work with the quantum systems.
Yeah, thank you so much for the introduction. Today I'll be talking about local minimum in quantum systems. This is a joint work with Anthony, who gave the first talk, John Presco, and Liozo. So we all hope that quantum computing can help advance physics, chemistry, and material science by solving the ground state of quantum systems. But at the same time, we also know that finding ground states is QMA hard. And hence, ground states are both classically and quantumly hard to find. And as a result of this QMA hardness, it also means that ground states are not always physical from a kind of a nature sense. Because if we assume that nature cannot efficiently solve NP hard problems, then it shouldn't be able to solve these QMA hard problems. And hence, nature should not always be able to find the ground states. In particular, when we try to cool down a many-body system in a low-temperature environment, like a low-temperature thermal bath, the systems will go to a local minimum of energy, which might not be the ground state. Where one can think of it in this way. So suppose the energy landscape look like this dashed line. And if we start in the left, then after cooling down, we might go to the ground state. But if we start on the right, then potentially under a certain condition, it might just get stuck in this suboptimal local minimum, which has much higher energy compared to the true ground state. And it would just get stuck there for maybe an exponential amount of time. In particular, for some physical systems, such as spin glasses, it is well known that systems almost always find suboptimal local minimum due to the energy landscape of these systems. So for these kind of systems where there's a lot of suboptimal local minimum that attracts the system and gets stuck there, ground states are physically irrelevant. And the more physical relevant object are these local minima. So from this motivation, it raises the following motivating question, which is the main question that we will study in this work. That is, how tractable is the problem of finding a local minimum in quantum system using classical versus quantum computer? So previously, there have been a wide range of works that study the problem of finding ground state. But here we replace ground state by hopefully a more physically relevant object, or more like nature would always find such a thing. And yeah, and this is the main question that we're going to set out to solve. In order to make progress in solving this question, we have to first provide a formal definition of what local minima are and provides a characterization of these local minima, so then we can talk about the computational complexity for finding them. And that's going to be the overall kind of outline of the talk. Particularly, I would first by giving a definition of local minima, and then I would talk about the computational complexity for finding them, and then conclude with some future directions. Let me begin with the first part. Suppose we are given some n-qubit Hamiltonian H that can be written as a sum of few body terms. A very natural way to define local minima is to consider any n-qubit state rho that has the minimum energy under any small perturbation to the state. One can think of it on the left top plot, where both of these 2 points, when you perturb them slightly, the energy is minimum. However, this definition depends on how we consider what perturbations we can take. So let's say we consider a family of perturbation given by P alpha that takes states to states and is parameterized by some high-dimensional vector alpha. In particular, we can consider these P alpha to be certain CP3 maps. For example, it could be some gate that we applied to the state, or it could also be some Lindbladian evolutions or some other unitary evolutions. Given a class of perturbations, an n-qubit state rho is an approximate local minimum under such perturbation if the energy of the state rho is less than or equal to the one after perturbing up to the small error term. So here, if we take epsilon to be 0, that becomes an exact local minimum. However, finding exact local minimum is very hard, even for classical optimization. So here we're going to focus on having epsilon that is inverse polynomially small. One should think of it as having this epsilon term. So one thing to note here is that suppose we have, like in the context of quantum machine learning, there's these notion of barren plateau, which are essentially think of it as a big flat energy landscape where there's a exponentially small tilt. So for those points that are on barren plateau, we would still call them an approximate local minimum, even though they're not exact local minimum, because they have these exponentially small, like you can go down by exponentially small, but if one only consider up to an epsilon error, then they're essentially flat. So to provide some more intuition about local minima essentially forms a subset of the entire n-qubit state space. And this subset would contain the true ground state. And this subset would also depend on what the perturbations are. Here we're going to focus on two classes of perturbation. One is motivated from a more quantum computing perspective, and another one is motivated more from a physical perspective. So the first one we call local unitary perturbation, which considers the space of states to be pure state. And the perturbations are essentially given by this form shown here. So we define a set of few-body Hermitian operator, HA, and these perturbations just correspond to we're evolving by taking a linear combination of these local terms and then evolving for a small amount of time. One thing to note is that any quantum circuit with a near identity 2-qubit gate, that is all the 2-qubit gates are close to identity, would form a local unitary perturbation to the first order, just by simple Taylor expansion. And yeah.
So I guess you're interested in reasonably deep local minima, right? Very shallow. So how do you first select those local minima?
So here, of course, we would like to find the deep one that are closer to ground state, but maybe we cannot find them. Maybe they're hard. So here, all the discussion were still at a very high level. I agree that in practice, we wanted to find the deeper local minimum, but maybe they're hard to find. So here we're just talking about finding a local minimum.
How much is this that you sort of allow kind of flexibility for trying to do because of how it is like in the future and system. So we have like you can only go in the positive direction, like sort of without try to look for the hardness and the hardness is sort of measured by approach. And then that's the system of the and if you look define some more statement that like only goes with
yeah, that's a good, you're asking like how realistic is this epsilon constraint? Yeah, so the one about barren plateau, the comment that I mentioned, if one set, say, epsilon to be 0 or exponentially small, then suddenly the problem of finding local minimum can be made very, very hard as like solving ground state. So in a way, that means that nature should not be able to find these exact local minimum. It should only be able to find some approximate local minimum due to some fluctuations. Yeah.
Do benefits exist at energies much below
So usually people think of it as barren plateau existing for like, say when the states form designs, which then the energy just becomes like the same as hard random state. Yeah, so you're asking if we're focusing on a low energy subspace, then does barren plateau exist?
Exactly. Like you can start with a product state which is much better than hard random.
Yeah, that's an interesting question. To my knowledge, I don't think there's an answer to that. It could still possibly have some other kind of plateau that causes it to be hard. So this is one definition of perturbation based on just Hamiltonian evolution and based on like a circuit picture. And this kind of perturbation actually defines a Riemannian geometry over the space of pure states. And it's essentially the same as the one that was studied around 20 years ago by Nielsen et al. On this paper called Quantum Computation as Geometry, where they define this Riemannian geometry by considering local perturbation or local unitary perturbation. And yeah, so this is quite a mathematically natural definition, but as we will see later, this definition has some problem. The second class of perturbation that we're going to consider is a more physically motivated one, and it's more connected to the previous talk. That is, if we consider these perturbations arise by thermal perturbation, that is, we're putting this quantum system into some cold thermal bath, and the perturbation on the system is caused by interaction with these thermal baths, then these perturbations should be described by Lindbladian dynamics rather than unitary dynamics like the previous one. And furthermore, these perturbations are generally irreversible. So they're not unitary, they're these Lindbladians, and usually energy leak out to the environment, etc. So in order to properly define these thermal perturbation, we're just going to take the formalism that Anthony talked about in the previous talk. That is, from modern quantum thermodynamics, there are two macroscopic properties that determine the thermal bath. The first is the inverse temperature, given by beta, how cold the environment is. And the second one is called characteristic timescale, which essentially corresponds to how long does the bath memorize things. In particular, in this talk, one should always have in mind that the temperature is very low, so beta is very big, and tau is also very long. So the thermal bath can memorize longer and then distinguish energy differences more clearly. So now under these beta and tau, we can write down the thermal perturbation, which are given by these thermal Lindbladians that was also discussed in the previous talk. Particularly, we consider a class of local operator given by these AA. One can think of it as the following. So we have the system, we have the environment, and the system and environment interact through these local operator. Think of it as maybe there will be some decay, and so photons will shoot out into the environment, etc. And through which the system and bath can interact. And given these local operator, it induces, because of the evolution, the environment induces these thermal Lindbladian that causes the system to evolve. So here we consider essentially these class of perturbations as the thermal perturbation. So as a summary of the definition, we define an n-qubit state rho to be an approximate local minimum of H if under small perturbation, the energy doesn't increase too much. And we also focus on two classes of perturbations. One is local unitary perturbation that is connected to this quantum computing quantum circuit picture. And the second one is thermal perturbation, which is connected to how an actual physical system interacts with the environment. So now with these definitions, we can start asking what is the computational complexity for finding local minimum. But before doing so, we have to talk about what's the problem. So here we say an algorithm solves the local minimum problem efficiently if for any n-qubit local Hamiltonian H and any local observable O, the algorithm can output the property O on some approximate local minimum of the Hamiltonian H in polynomial time, up to inverse polynomial error. As we can see, this problem is purely classical. The input is just a classical description of the Hamiltonian and some local observable, and the output is a single real value that tells us about the property of one of these local minima. So for example, if there's many, many local minima, then the algorithm, we would still consider the algorithm to succeed if it just outputs a value for one of it. So it's more like a relational problem. So here, yeah, so here we consider the case when there could be, one could output any local minima. So you could start from any point, and if that goes to this local minima, then you output that. That's fine. If you start from a different point and it goes to this local minima and you output that, that's also fine. So this is more like a much simpler problem in a sense that it's easier to solve. So if one could focus on having an initial state and then talk about cooling until a certain point, and then that would be a different problem, and that could potentially be harder in the sense that there could be more quantum advantage. But here, this only focuses on you just need to output any. Yeah, so here, because we considered the epsilon to be just some inverse polynomially small, so it could be epsilon 1 and epsilon 2, and you just consider taking the minimum of them, and now they're the same. So yeah, so I would say in a way we set up this problem so that it's as easy as possible and still makes sense. So then we can talk about, yeah, so then the quantum advantage is stronger, I would say, that we're going to show later. Yes, definitely one could also consider a problem, which is a classical input and quantum output problem, where the goal is to output a state that's close to a local minimum under trace distance. But then that would not be a classical input output problem, and then we can no longer talk about quantum advantage. Yes, but how would a classical computer talk about a quantum output, which is a little bit tricky. So you mean the approximate local minimum epsilon? Yeah, so actually even classically, if one considers exact local minimum, that's way beyond P. That's super hard. Yeah, we are always aiming for efficient algorithm. So that's why there is an epsilon.
Make it a little bit stronger than any observable that is
yeah, so actually, what we're going to show on the quantum side, the quantum algorithm is going to be able to find a state that's very close to a local minimum. Yeah, so for any observable, we can. Yes. So the restriction is mainly to make it easier for classical, and yet say that this is still hard for classical.
Allowing for it to run per state. Energy is the correct stability criterion, the free energy should be a stability criterion.
Yeah, so here as we're going to talk about, we're always considering beta to be very big. So the temperature is like very small, and hence like the entropy correction term is negligible. But yes, I agree that if your focus is on, say, a constant temperature, then perhaps the right quantity should be the free energy rather than the energy of it. Yeah, so classical shadow will allows one to predict all local observable efficiently. And that's also, so in a way one could think of local observable as being easier for classical methods. And hence we're going to show that this is still hard for classical. So. Yeah, so we're always going to consider these, one could always think of it as these local interactions are, say, like 2-qubit polys. So in a way we kind of remove that because we're just focusing on some fixed set of terms. Okay. Oh. Yes. Yes, with respect to the energy. So the observable is just there to, yeah, it's the local minimum of the energy, and we're just trying to predict some property of the local minimum. You mean if one consider constant temperature and one try to, yeah, so one of the thing is it's not clear how to estimate free energy efficiently because the entropy term is hard to estimate. So it's not clear how one could efficiently have an efficient algorithm that could find a local minimum of free energy. That's still in a way, an open question. Okay. So yeah, so hopefully through these questions, the definition of these local minimum problem is now clear. And then we can talk about the computational complexity. The first proposition focuses on the case for local unitary perturbation, where we consider the perturbation to be given by quantum circuits that are close to identity. Here we can show that the problem of finding local minimum under these perturbations is classically easy. It's in BPP. And the reason of this proposition is the following lemma, which essentially just kind of restate this known result on barren plateau. That is, for any local Hamiltonian edge, random state will be a local minimum of H, or will be an approximate local minimum for an approximation error that's even sub-exponential in system size under local unitary perturbation. Essentially, most of the states on the quantum state space will be on this plateau. And hence, if we just consider a random state, it will already be a local minimum under this kind of definition. And hence, a random state behaves exactly like a complete mixed state, and hence the problem is easy classically. So of course, one can ask, then what if we try to start at a point that's very close to the ground state, and how does the complexity changes? But then there's a lot of subtlety that arises. Like, for example, how do you quantify where you start and so on? Like, if I only start at all zero state, then does it become hard and so on? I think all of these are valuable and important questions, but we're not going to address them here. However, as we define, the local minimum problem is easy classically if we focus on local unitary perturbation. And what we're going to focus on more is how does things change when we change from local unitary perturbation to thermal perturbation. So the first theorem that we showed is that the problem of finding local minimum under thermal perturbation is quantumly easy. And this can be strengthened to be finding, say, just outputting a state that is very close to local minimum, not just estimating properties. Yeah. The algorithm is essentially like given, yeah, so go back to the problem. So now after we see this and see the local observable, we just estimate the trace of O divided by 2 to the n. And that's it. So, yeah. Trivial. It's not even easy, it's trivial.
But that might not be a local minimum.
So maximum mixed state, I mean, here we're focusing on pure state. Actually, yeah, there are ways to strengthen it, but essentially if you just output like a there are these pseudo-random state construction, and if you consider some pseudo-random state which can be described efficiently classically, then that will be a local minimum. With high probability, yes.
So, but you don't care if you just pick the wrong answer.
So yeah, so here there's always a with high probability involved, because I mean, quantum algorithms are always probabilistic. So
it's still worth it for any.
Yes. 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 So this lemma that I showed is true for all H. No matter what the Hamiltonian is, a random state, if you try to perturb it in any local unitary perturbation, the energy will only changes by an exponentially small amount. And this holds with 1 minus an exponentially small probability. So like it's really high probability. Yeah. Okay. So in order to prove that the problem of finding local minimum under thermal perturbation is quantumly easy, we essentially combine the algorithm that Anthony talked about in the previous talk and gradient descent. So we just look at all possible perturbation and then calculate the gradient and choose and just literally do gradient descent using these thermodynamic algorithms. In order to prove that such an algorithm converges, we have to utilize some property of the thermal Lindbladian. So in particular, if these thermal Lindbladians are highly non-analytical, then it could be that gradient descent doesn't really converge to the local minimum. However, because these thermal Lindbladians have some nice second derivative, we can use them, and then by combining with the standard kind of gradient descent convergence proof, we will be able to obtain this theorem. So now we see that this problem of finding local minimum under thermal perturbation is quantumly easy. We can ask, is the problem also classically easy? And to answer that question, we're going to consider a class of Hamiltonians on a 2D lattice based on a modified version of Kitaev's circuit Hamiltonian construction. So given some polynomial-sized quantum circuit C, there will be a corresponding Hamiltonian HC on a 2D spin lattice. In particular, the ground state of the Hamiltonian HC will encode the output of the circuit C. And hence, because the ground state encodes the output of the circuit, finding the ground state of such Hamiltonians is BQP hard. However, that's for finding ground state, and our question is for finding local minimum. Because finding ground state, we know it's pretty hard. So if it's BQP hard, maybe finding local minimums can still be much, much easier. Yeah, so yes. So there are also ways to construct this so that it becomes QMA hard, but we're going to focus on a modified version so that it's BQP hard. Yeah, so essentially in QMA hard Hamiltonians, there will be tons of local, like exponentially many local minima, and yeah, and we're not going to use them. We're going to use these other modified class. Yes. So there's no contradiction here. So now the question is finding local minimum of HC easy classically? Maybe there are some classically easy local minimum that are lurking in this exponentially large space, like in the previous case for local unitary perturbation. We can consider these class of Hamiltonian, the same class, and focus on finding local minimum under local unitary perturbation, and that will be classically easy because of this barren plateau. But now we are going to focus on thermal perturbation, and what we're going to show is the following theorem, which is that for these class of Hamiltonians, all the approximate local minimum under thermal perturbations are close to the true global minimum. And hence, another pictorial way to think about the theorem is that the energy landscape of these Hamiltonians that we're going to look at has a nice ball shape. So no matter what initial state you start with, after cooling it down, it would just go to the ground state, starting from anywhere. Yeah, so for these class Hamiltonian, they will be close in terms of the trace distance.
So why does this break down to QMA? Like the weakness of one qubit weakness.
Right. Yeah. So that's what. So we're really using some special class of Hamiltonians here. If one consider QMA hard Hamiltonian, then this picture will not be true. It would be more like the picture from a while back where there's many suboptimal local minimum and only one of it is the ground state, or some of it is the ground state. Yes. Oh, I see. Possibly, but not entirely clear. Yeah. Because in this proof, we're going to utilize some property of these local jump operator to show that the energy landscape looks good. So if we now, if you add more, like if you have this local and then you add more, then the energy landscape is just going to get better. It's going to get more complex or more bowl shape. It's never going to get worse. Yeah. Okay. So what I'm going to do is I'm going to spend some time to talk about how the theorem is proven, particularly showcase some properties of quantum thermodynamics. One thing to note is that the theorem is really suggests that for these class Hamiltonians, there's no barren plateau and there's no bad local minimum, and we're going to see how the theorem can be used to claim that finding local minimum under thermal perturbation is classically hard. So now first, we're going to begin with the proof idea of this theorem that showcases nice ball shape. So first, like what I'm going to do is I'm going to consider some property of these quantum thermodynamics. So let's say we focus on some local operator A that talks about how system and environment interacts. And given such a local operator, one can think of it as this A is just like Pauli operator, like X on the first qubit or Y on the third qubit, etc. The thermal bath, the thermal environment, will induces a Lindbladian after integrating out the environment on the system, where this Lindbladian will have a continuous set of Lindblad jump operator. So this Lindblad jump operator depends on what the Hamiltonian is, depends on what's the local operator, and also depends on this characteristic time scale. In particular, for people that are not familiar with Embodian, one can think of it very intuitively as the following, which is every time we're going to sample one of these jump operator via some distribution, and we're going to take the jump operator, apply onto the state, and then normalize it. So that's when a jump happens, or the system just evolves under its unitary dynamics. But when a jump happens, that's the intuition. So once you think of it as we're going to apply this A hat A onto the system, and hopefully it will decrease the energy of the system. Note that this continuous set of Limblot jump operator, it has an index omega that goes from -infinity to infinity. And this index omega, once you think of it as having an unit of energy. And essentially what omega does, kind of intuitively, is that it measures the energy difference. It talks about the difference of two energy levels. So to provide more intuition of the jump operator, let's first we focus on the spectrum of the Hamiltonian. So there will be some dots that corresponds to different energy level. And here we will be focusing on the difference of them. So there will be many different difference of the energy level, which is known as the Bohr frequency of the Hamiltonian. So B of H just correspond to energy differences. We just subtract two energy level. So now what we're going to do is we're going to consider these local jump operator. Say it's a poly X on the first qubit. We write it out in terms of the energy eigenbasis. And that's what this first equality becomes. So we have this exponentially large matrix correspond to different energy level, EI and EJ, and there will be some matrix element on them. Now what this Limblot jump operator does is it's essentially picking out certain transitions. So the difference between AA and the Limblot jump operator with a given omega is that there's this square root kind of delta function inside. So this delta tau is just an approximate version of delta function. So for this talk, one could just think of it as it's just a delta function. So here what this Limblot jump operator does is that given an omega, it picks out all the energy transition, like EJ to EI, that have an energy difference of omega. And all of the other things would just get set to 0. So I hope that there's a simple way to just easily derive this equation from the definition of these Limblot jump operator. So the key idea here is that while the original local operator, like these poly X on some qubits, might have matrix element between EJ and both lower energy and higher energy. And hence, if you just apply these local operator to the state, it doesn't really decrease the energy of the system. If we now apply this Limblot jump operator onto the state for some omega less than 0, it would now only induce the transition from EJ to a lower energy state. Because if omega is 0, we see that all the terms that go from EJ to higher energy, EI, would get killed. And only terms that go from EJ to essentially EJ minus omega will survive. And hence, by considering these Limblot jump operator, essentially creates a dynamics that only pushes eigenstate to lower energy states. And that's why it would eventually lead to having this nicer landscape. So now from this picture, we can see that if for all energy eigenstate EJ, there exists some local operator, like some Pauli operator AA, and some lower energy state EI, less than EJ, such that the matrix element that go from EJ to EI is not equal to 0, then the whole landscape will have no suboptimal local minima. Sorry? It's not really. Like when you have a local operator like x1, then the Hamiltonian will determine what these matrix elements are because they're just the. Yeah, we're going to end up talking about what these matrix elements look like and why it has this nice property. In a way, yeah. So this is actually very, very similar to the consideration in classical combinatorial optimization. If one considers the energy eigenstate to be some bit string, and consider these local operator to just be some bit flip operation, then what it's essentially saying is that for all bit string, there exists some bit flip operation, like local bit flip operation, that takes it to a lower energy or lower cost function bit string. And hence, like in the classical setting, it's pretty clear that there will be no suboptimal local minimum if this criteria holds. But essentially, using the language of thermodynamics, it generalizes to the quantum setting.
They're not, they're like opposite of they're non-constant.
Okay. So now this is like the intuition behind this claim. So now given some circuit C with a unitary UC that is just a product of single qubit and 2 qubit gates, we're going to construct the Hamiltonian. So this is, hopefully people are very familiar here now. This is just a standard, it's just a modified version of the Kitov circuit Hamiltonian construction. The Hamiltonian HC will have the H clock, which checks whether the clock is ticking correctly. There's the H prop, which checks whether the propagation is doing correctly. And then there's H in that checks the input. So the idea here is that the ground state of the Hamiltonian will be given by this form shown here, where there's the first n qubit, and then there's these clock register of t qubits. And yeah, and there's a strange part which comes from this binomial distribution that we're using, that's square root capital T choose small t, which I would describe why we make that choice later. There's another important point, which is we're going to set up the Hamiltonian so that the strength of the clock Hamiltonian is much bigger than the strength of the propagation and much bigger than the input. Oh, yeah. So the idea here is that we're going to prove that first, there are no suboptimal local minimum if we focus on the clock itself. Then we're going to show that in the ground state space of the clock Hamiltonian, there are no suboptimal local minimum for the sum of them. And then the last step is in the ground state space of the first two, there are no suboptimal local minimum in the sum of the three. So these three statements combined doesn't really give the desired result because it doesn't, because usually in these kind of thermodynamic setup, there's going to be thermal fluctuations and there will be error everywhere, in particular for the higher energy states. So we're not going to always be talking about the ground state space. And in order to really combine them, we actually have to require that the Hamiltonians that we're talking about here have a large Bohr frequency gap. So what that means is if we consider the collection of the energy differences, the smallest difference of the energy differences must be sufficiently large. It's a little bit but I hope it's kind of clear from before, because as we have seen from the thermodynamic picture, it's always talking about the energy differences. And hence we need to have some kind of these energy differences gap so that when we sum up different terms that doesn't really commute with one another, it doesn't mess up these energy differences gap. Just inverse polynomial. Inverse, it's just a small. Yeah, it's not that large, sufficiently large. But... Yes. Sorry? Yeah, there will be a lot of degeneracy because yeah, so either the energy differences is just strictly zero or it has to be sufficiently high, up to some inverse polynomial error. Then things will be more well behaved. Yes. Yes. Yeah. So in a way, I think that we think the original circuit Hamiltonian construction has this property, but we don't know how to properly prove it. So we ended up making some modification to ensure that that's true. Yeah, there could be large degeneracy. Like it could be many that zero. Yes. So it could be that there are two different energy differences that are the same, but then so that's the difference of the energy differences would be zero. But then if they're really different, they have to be. Yes. Or maybe the level has to be sufficiently distinct.
This is not the given value. This is initial, right? You don't know the given value.
Oh, actually, whenever I talk about there are no suboptimal local minimum, there are this notion of Limbladian that comes in.
One under the evolution of the embodiment.
Yes. I mean, yeah.
The notion of the generalized spectral that we have.
Oh, yeah. This notion, there's no Limbladian. Yeah, there's nothing to do with Limbladian. This is just a property of the spectrum. So more precisely, the modification we make for the Hamiltonian for the input, it's the standard one. But for the clock one, we have to, usually the standard definition is that it has a uniform local terms. We now have to make them to be non-uniform and decreasing in t. It's because in the original definition, local excitation can actually move around without changing energy. Now by making it non-uniform, we essentially make this plateau like have a slight tilt, and hence there will be no plateau in the landscape. And for the propagation, we have to, usually it's frustration free and gives rise to a uniform superposition. Now we have to make it non-frustration free and yields this weird binomial distribution so that the energy spectrum of the propagation Hamiltonian is now just integers, like 0, 1 to t. So then we can talk about Bohr frequency very easily. It's just all integers, and hence the Bohr frequency gap is just 1. Yeah. Yeah. It's moving through inside. Yes. So together, by making modification to the circuit Hamiltonian construction, we can show that these Hamiltonians have a large Bohr frequency gap, and all these three statements hold, and hence there are no suboptimal local minimum in these Hamiltonians. And that's how we establish the theorem. And using the theorem and the fact that finding ground state of these Hamiltonians is BQP hard, we can essentially show that if one can find the local minimum efficiently, then because local minimum are close to ground state, so then one will be able to find ground state efficiently. And hence this problem of finding local minimum under thermal perturbation must be classically hard. And one corollary of this is that there are some 2D Hamiltonians where if we take some optimized classical ansatz like neural network or tensor network, it can be strictly improved by simulating quantum thermodynamics. So this is just the overall picture where finding local minimum under local unitary perturbation is trivial for classical computation. But if we now consider thermal perturbation, which is more physical, it is now universal for quantum computation. And a kind of a funny way to think about it is that if we have a very good refrigerator, it's a universal quantum computer. And now I would conclude with some open problem. So here in this work, we consider these local minimum, which are essentially quantum states that are indistinguishable from ground states under some small perturbation. But we can consider, instead of just small perturbation, what if we consider, say, all computationally efficient perturbation? So it raises this following question, which is, could we efficiently find states that are indistinguishable from ground states under quantum algorithm with some bounded runtime? Like maybe the runtime is bounded by some capital T, or maybe it's all polynomial time. So I was thinking about this for quite some time, but couldn't really figure it out. Maybe some of these recent progress in pseudo-randomness could help answer this question, which could be very interesting. Another very important direction is that our result shows that there's quantum advantage in computing properties of system that is being cooled in a very low temperature. However, in all practical setting, the temperature is just some constant. It's never going to like decrease in system size. And hence, important open question is there a quantum advantage in computing properties of system that thermalize at a constant temperature? So this is still open. However, in the next talk, Thiago is going to talk about the advantage in sampling from such systems. So there is quantum advantage when we consider sampling, but right now we don't know if there's quantum advantage in computing property. So to conclude, while finding ground state is classically and quantumly hard, in this work, we showed that finding local minima in energy is classically hard, but quantumly easy. So hopefully it could provide a new way to look at quantum advantage in studying low temperature physics. That's it for our talk. Thank you so much for listening.
So let's take the questions offline because we're over time. We'll come back at 2 o'clock here for Thiago's talk. And also tomorrow, 3:15 to 4:45, we have open problem discussion, which will not be recorded in any part, and the recording is not permitted. So if you have interesting open questions in mind, please nudge either me or Bill. You can talk to us or send us an email. All right, so see you at 2.